Okay, welcome to the GATE BT Express Series Part 4. So we have 5 questions here. Question 1. The mammalian cells in active growth phase were seeded at a density of 1 into 10 raised to the power 5 cells per ml. After 72 hours, 1 into 10 raised to the power 6 cells per ml were obtained. Population doubling time of the cells in hours is up to 2 decimals. So let's write the differential equation that governs the cell growth. It is rate of change of cells over time is proportional to Kn. Right? Say let's integrate this equation. It is dn over n equal to k times dt t, that is changes from time 1 to time 2. Here say 0 hours to 72 hours. And the number of cells becomes n1 to n2, that is 10 raised to the power 5 cells over ml to 10 raised to the power 6 cells over ml. Let's assume base is 1 ml. Therefore there are 10 raised to the power 5 cells and 10 raised to the power 6 cells after 72 hours. Therefore the integrated expression will be dn by n ln n. After applying limits, ln n2 over n1 is equal to k t2 minus t1. t2 minus t1 is 72 hours minus 0 hours is 72 hours. Ln of n2 is 10 raised to the power 6 divided by 10 raised to the power 5 is equal to 72 times k. Let's get the value of k. K is equal to 10 raised to the power 6 over 10 raised to the power 5 is 10. That is ln 10 by 72. This is the expression for the rate constant k. We need to find the doubling time. What is doubling time? That is, if there are n cells, after this doubling time it becomes 2n cells. Let's plug in this condition, that is n becomes 2n after a time t doubling. In this equation, ln n2 over n1 is equal to k dt. So ln of 2n over n is equal to k times the time is t doubling. Therefore ln 2 is equal to k. But we have found the value of k, which is equal to ln 10 by 72 times t doubling. The units for k is hour inverse, because hour goes to denominator, 1 over hour. Therefore t doubling time is equal to ln 2 over ln 10 times 72 hours. So the value ln 2 over ln 10 into 72 hours is say 21.67 hours. Calculated using scientific calculator. So the doubling time of the cells in hours is 21.67 hours. Next, moist heat sterilization at 121 degrees Celsius follows the differential equation model, that is dn over dt is equal to minus kd times n, where kd is the specific rate for, that is rate constant for cell death. If kd is equal to 1 over minute, the time in minutes required to reduce the number of spores from an initial value of 10 raised to the power 10 to a final value of 1 is. Again we have a differential equation, that is dn over dt, rate of change of cells is equal to minus kd times n. First order differential equation with respect to n. Let's solve this. Therefore dn over n is equal to minus kd times dt. Let's integrate. We need to have the limits, that is say from t1 to t2 it makes the cells to go from n1 to n2. dn by n is ln n, and applying limit we get n2 over n1 is equal to minus kd times t2 minus t1. let's plug in the values we know. That is, initial value is 10 raised to the power 10 cells. So n1 is equal to 10 raised to the power 10 and n2 is equal to 1 cell 1. Therefore ln of 1 over 10 raised to the power 10 is equal to kd. Kd is 1 over minute minus 1 over minute times the time required to reduce. Let's assume t1 to be 0. That is the starting point. We assume a basic time, that is 0 minutes. Therefore t ln 10 raised to the power negative 10 is equal to minus t by minute. So which is nothing but minus 10 ln 10 equal to minus t over minute. Minus 10 times ln 10 is 2.303, which is equal to minus t over minute. Let's cancel the negative sign on both sides. Minus minus cancel out. Therefore 23.03 minutes is the time required to make the number of cells from 10 power 10 to 1. So the time required to reduce the spore count from an initial value of say 10 raised to the power 10 to a final value of 1 is 23.03 minutes. Time in minutes, so it's 23.03. Next, third one. A microbial strain is cultured in a 100-liter stirred fermenter for secondary metabolite production. If specific rate of oxygen uptake is 0.4 hour inverse and oxygen solubility in broth is 8 mg per liter, then the KLa, that is resistance to mass transfer or volumetric mass transfer coefficient in 1 over second of oxygen required to achieve a maximum cell concentration of 12 gram per liter is. So we need to find the value of KLa where the maximum cell concentration, say X max, is equal to 12 gram per liter. So let's write down the equation. We have the condition, say OTR is equal to OUR, where OTR is the oxygen transfer rate. So oxygen transfer rate is nothing but the number of moles of oxygen is being transferred from by the process of sparging. We sparge air through a sparger. Either in form of air or pure oxygen would be sparged through the sparger. So the Na is equal to resistance times the concentration difference. Resistance is KLa. The concentration difference is C star minus C, where C star is the oxygen concentration, that is saturation, and C is the concentration of oxygen or the dissolved oxygen in the broth, is equal to OUR. OUR is the oxygen uptake rate, how much oxygen is being consumed by the cells, which is equal to Q0 times X, where Q0 is the specific oxygen consumption rate, that is how much moles of oxygen is being consumed by one cell, it is per cell. So we need to find maximum cell concentration, that is X max. Then we need to know when this X, that is how the cell population, reaches a maximum cell concentration. Cells will reach a maximum cell concentration when all the oxygen that is being supplied is being consumed. That is, there is no free oxygen in the broth. Therefore, the dissolved oxygen in the broth is 0. That is, C is equal to 0. When this condition is met, therefore K is the X max. That is, X is the X max. KLa times C star. C star is the oxygen solubility in the broth is 8 mg per liter. The constraint C is equal to 0 is applied. And Q0 is the specific rate of oxygen uptake is 0.4 hour inverse given. 0.4 over hour times X max. X max is 12 gram per liter. Let's write in consistent unit, that is 8 mg per liter is equal to 0.4 per hour into 12 gram per liter. 1 gram is 1000 milligram per liter. Therefore, KLa would be equal to mg per liter cancels out. KLa will have the units of hour inverse, that is 0.4 by 8 into 12000 hour inverse, that is say 0.12 times 0.1 to 600 hour inverse. But KLa has to be reported in units 1/second. So KLa in seconds, that is s raised to the power -1, is equal to 600 per hour into 1 hour as 3600 seconds. So which is equal to 0 cancels out, 6 ones are 6 6 are, so 1 by 6 second inverse. Therefore KLa is equal to 0.167 second inverse. So the value of KLa, or the resistance to the mass transfer or the oxygen transfer, or the volumetric flow rate, volumetric mass transfer coefficient in 1/second of oxygen required to achieve a maximum cell concentration of 12 gram per liter is 0.167 1/s. If we have a mathematical problem, that is 1 plus r square plus r cube plus up to infinity is equal to 1.5, then 1 plus 2r plus 3r square plus 4r cube plus up to infinity is dash. So okay, let's solve this here. Given is 1 plus r square plus r cube up to infinity is equal to 1.5, right? Let's take 1 to the other side. Therefore r plus r square plus r cube plus up to infinity is equal to 1.5 minus 1, that is 0.5. Let's take r common. Since it's a geometric series, it has a common ratio r. We can find this common ratio by T2 by T1, that is term 2, that is r by term 1, 1. R by 1 is r, which is equal to T3 by T2, that is term 3 is equal to r square divided by term 2 is equal to r. Therefore r square by r is equal to r. 1 plus r square plus up to infinity equal to 0.5. And the expression in the bracket is nothing but the expression given, which is equal to 1.5. So the value of r is 0.5 over 1.5, which is nothing but 1 by 3. And I have initially mentioned that this is a geometric progression series, and we can write this series in a say form like this. Say 1 minus x raised to the power -1 is equal to 1 plus x square plus x cube plus up to infinity. So this is a similar series. So we can write this all 1 plus r square plus r cube plus up to infinity is equal to 1 minus r raised to the power -1, right? And we need to find the value for another series, say 1 plus 2r plus 3r square plus 4r cube up to say infinity has to be found. Let's see. Let's differentiate this equation with respect to r. Differentiation of 1 will result in 0, and differentiation of r will give 1. R square 2r, r cube 3r square, then r power 4 will result in 4r cube, and so on. So the value of the expression that we need to determine is nothing but the differential expression. We need to differentiate this equation with respect to r. Up to infinity is the required answer we need to find. On differentiating this, instead of differentiating this equation will give this form. say 1 plus 2r plus 3r square. Let's write this short form, say 1 minus r raised to the power minus 1. Now differentiate this thing, minus 1 into 1 minus r raised to the power minus 2 into differentiation of minus r is minus 1, r by r is 1 is the required answer. Minus into minus plus. So it's 1 minus r raised to the power negative 2 is the required answer. So 1 minus the value of r which we initially found, say 1 by 3. So 1 by 3 raised to the power negative 2 is the required answer. Therefore answer is equal to 1 minus 1 by 3 is 2 by 3 raised to the power negative minus 2. Let's reciprocate, that is 3 by 2 raised to the power 2. On squaring 3, 9, squaring 2, 4, 9 by 4. So 4.5 by 2, that is 2.25. So the value of this equation, so this expression is nothing but the differential, that is d by dr of this equation, which results as 2.25. And finally we have this problem, that is yeast converts glucose to ethanol and CO2 by glycolysis as 1 mole of glucose C6H12O6 giving rise to 2C2H5OH plus 2CO2. Assuming complete conversion, the amount of ethanol produced in gram from 200 grams of glucose is. So from the equation we can see that 1 mole of glucose will give rise to 2 mole of ethanol ETOH. Let's write in terms of mass. 180 grams will become 2 into 46 gram, which is equal to 92 gram. Therefore yield coefficient YP bar S, that is grams of product formed per gram of substrate consumed or reacted, which is equal to 92 grams of ethanol per 180 grams of glucose, which is equal to say 0.51 grams of ETOH per gram of glucose. But we need to find the amount of ethanol produced from 200 grams of glucose. So multiply this value into 200 grams. Therefore answer is equal to 0.51 grams of ethanol per gram of glucose times 200 grams of glucose. Say 2 5s are 10, 2 1s are 2, 0 0 decimal point grams of ethanol. Say we produce about 1 or 2 grams of ethanol per 200 grams of glucose. So we finish this session by writing down all the formulas. For these mammalian cells in the active growth phase, we use the formula, say ln n2 by n1 is equal to k T2 minus T1, and one more formula, that is ln 2 is equal to k times T doubling. Which we got from the integration of the first order equation, which involves n, and the expression for doubling time. Next, for sterilization, we followed a similar integration with respect to n, and got ln say n2 over n1 is equal to minus kd times T2 minus T1, and we found the time for sterilization. Next, in third question, we found that OTR is equal to OUR and KLA into C star minus dissolved oxygen would be 0, must be 0 when X becomes X max. And finally, this expression is nothing but a series in form of 1 minus r raised to the power minus 1, whose sum of series is 1 minus r raised to the power minus 1. And differentiating this series, we get a series whose sum has to be found, that is 1 plus 2r plus 3r square plus 4r cube, which we got 2.25. And finally, we just calculate the yield coefficient YP bar as, that is grams of product formed per gram of substrate consumed, and multiply by the amount of substrate that is fed to get the desired amount of product that is being formed. That is here 1 or 2 grams of ethanol is formed. Thank you.